Earth Systems 3209, Unit 2, Historical Geology. Text references can be seen in Chapter 6, Chapter 8, Appendix A, and Appendix B. Unit 2, Topic 2.3, Interpreting Cross-Section Diagrams Using Relative Dating Principles. This presentation will focus on our last presentation where we investigated relative dating principles and how they're used to relatively date age of geologic events. This lesson will focus on demonstrating how relative dating principles and different geologic concepts can be used to determine the history of formation of sample rock sequences, which we will refer to as cross-sections. Using relative dating principles to interpret geologic cross-sections. The relative dating principles that were discussed in the last presentation, they include the law of principal superposition. As a review, the principal superposition states that a sedimentary rock layer is older than all the rock layers above it and younger than all the rock layers below it, as long as the rock layers are undisturbed. So therefore, the lower in the sedimentary sequence you go, the older the rock layers will be. The principle of original horizontality states that when sedimentary layers are laid down, deposited at the bottom of an ocean or in some aquatic environment, that all the sedimentary layers are always laid down in horizontal layers originally. If you see sedimentary layers that are inclined, tilted, or folded, that must have happened at some time after the sedimentary layers were originally laid down in a horizontal position. Number 3, the principle of cross-cutting relationships demonstrates that any rock layer that cuts across another rock layer must be younger than the layer it cuts across. So this applies to igneous intrusions and also can apply to geologic events such as faulting. The principle of inclusions states that any rock layer or rock unit that is included within another rock unit must be older than the rock unit it is located within. And number 5, unconformities are buried erosional surfaces. When we look at the 3 different types of unconformities, an angular unconformity would have the layers below the erosional surface inclined at an angle, hence the name angular unconformity. A disconformity would show that the layers beneath the erosional surface are horizontal. Therefore, they are discontinuous, they are eroded, then more horizontal layers are deposited again on top. So a disconformity would have layers above and below the erosion surface located in a horizontal position. And a nonconformity exists when you have either igneous rocks or metamorphic rocks that are eroded, and they are later deposited and buried by sedimentary layers. So in this case, a nonconformity would show an igneous or metamorphic rock with an erosional surface buried by sedimentary layers. When we look at interpreting cross-sections, there are several rock symbols that we need to be familiar with. The first layer is sandstone. Sandstone is represented by dots located within the rock unit in the diagram. Next, we have limestone. Limestone is indicated by bricks located within the rock unit in the diagram. Shale would be demonstrated by showing dashes, and in some cases, dashes with little dots in between. When we look at coarser grained sedimentary rocks, such as conglomerate, we will see a diagram where you have round rock fragments within the diagram. Sometimes these rock fragments are a little larger. And in this case, we can see the rock fragments could also be round in appearance and a little larger. So that would be a good representation of conglomerate. Once we look at igneous rocks, granite or intrusive igneous rocks are generally represented by plus signs and sometimes can be represented by X's or even little dash marks. But in this legend, we see igneous intrusive rocks represented by plus signs. Volcanic igneous rocks are generally located on the surface and are represented by shaded in dark areas. Also in our diagrams, we will see contact metamorphism represented by X's. Some of the diagrams that we'll look at, the contact metamorphism is not as clear, so I will mark in where the contact metamorphism is located, and I will represent this on the diagram using X's. Let's look at a first example. Using relative dating principles, we can interpret geologic cross-sections. So if we look at the cross-section below, we can see that we have rock layer A, C, D, and E, all laid down in flat horizontal layers, with rock unit B passing up through. And also we have a dark line which represents a fault, fault F, cutting up through. In the legend, we see that sandstone, again, is represented by dots. Limestone is represented by bricks. In this case, contact metamorphism is represented by little hair-like structures, but generally they are represented by X's in diagrams. Shale is represented by your X's, and igneous rock in this diagram, according to the key, are little V's that are distributed throughout. And in this case, the V's would stand for volcanic rock. Some diagrams you see volcanic rock represented by a shaded area. So if we look at the diagram above, we will notice that the contact metamorphism will be located on the outsides of rock unit B and are represented by the X's that I am drawing in on the side. This would represent as the molten igneous rock passed up through the surrounding rock layers, it would have burned or baked the surrounding rock. And those are represented by the X's, which represents contact metamorphism. If we look at putting the layers of rock in sequence, we look at rock unit A. Rock unit A in the diagram represents sandstone. So rock unit A would be sandstone. Rock unit B in the diagram, according to the legend, would be an igneous rock unit. Rock unit C, which is represented by dashes, and the key would represent shale. Rock unit D, which is bricks, would be limestone. Rock unit E, again, which is represented by dots. Some of these dots are a little larger, but for the most part, conglomerate is not in our legend. So again, rock unit E would be sandstone. Rock unit F, or actually geologic feature F in this case, represents a fault. And X would represent an igneous intrusion. An X in the diagram is represented out here on the outside. In actual fact, the igneous intrusion would have contact metamorphism represented by the X's. So if we look at another historical walkthrough of a cross-section, we can see several different common questions that can be asked on any cross-section. Some of the common questions include the age of one rock unit compared to another. So if we come to the diagram, we could be asked to compare, for example, rock unit A, which is the magma which solidified into an igneous intrusion, and we could compare this rock unit to any of the rock units that it cuts across. Therefore, that would demonstrate that rock unit A would be younger than the rock units in which it cuts across because of the law of cross-cutting. Also, we could use rock unit B, and we can compare it to any of the rock units down below. For example, in this case, rock unit N. We would know that rock unit N would be older than rock unit B if the layers were undisturbed because of the law of superposition. So it is common that questions are asked to compare one rock unit compared to another rock unit and use your relative dating principles to determine which one is older and which one is younger. Hence, you find the age of one rock unit compared to another. The second question that is commonly asked in these questions is determine whether an igneous rock unit is intrusive or extrusive. Intrusive means it formed inside the Earth, whereas extrusive means it formed outside on the surface of the Earth. And the key here is in the contact metamorphism that surrounds the igneous rock layer. For example, in this diagram, rock unit A represents an igneous rock layer. Surrounding rock unit A, we would have, in this case, you could just barely see the little dash marks going around rock unit A, but on most diagrams we would see a series of X's that would completely separate or surround rock unit A. And these X's represent contact metamorphism. And they will continue right around the full rock unit. So these X's represent contact metamorphism. If you find contact metamorphism completely surrounding all the way around the igneous rock unit, that will give you an indication that this rock unit did not make it to the surface. Therefore, the rock unit will be called an igneous intrusive rock layer. If it made it to the surface, we would only see contact metamorphism on the bottom of the igneous rock unit and not on the top. The third question commonly asked is to identify folding or faulting in a cross-section. When we look at this cross-section, we do see several layers that were originally horizontal, according to the law of original horizontality, but in this case they are tilted. So these layers could be one side of a folded region, where the layers could show folding all the way around. In the situation below here, below the erosional level, we also see steep angles. The layers are steeper, inclined. They can also represent one of the limbs on a fold. But in the diagram here, represented by H, we do see a fault. And the fault cuts up across rock units E, rock unit G, rock unit L, and rock unit C. If the fault cuts through these rock units, it would mean that the fault would be younger than those rock units. So questions relating to folding and faulting are commonly asked in regards to these cross-section diagrams. Another question that could be asked is to identify cross-cutting or identify igneous rock units and faults. And those topics I've just previously discussed in relation to the diagram. You could also be asked to identify contact metamorphism. And generally speaking, contact metamorphism will be surrounding igneous rock units and represented by X's, as pointed out here, surrounding rock unit A. Another question that could be asked concerning these diagrams are questions concerning unconformities. And unconformities are buried erosional surfaces. In this diagram, I see 3 common unconformities. Actually, maybe 4. If we look right here, and if rock unit E is an igneous rock unit, then the boundary between rock unit E and rock unit G would represent a nonconformity, where E was once eroded and deposited and buried by G. Also, the rock boundary between rock unit C and rock unit M would show an angular unconformity. In this case, it would be an angular unconformity because rock unit L, which is the green layer, rock unit C, which is the brown layer, are inclined at an angle, and it's cut off by the boundary right above it. And then a layer M is deposited on top. So the buried erosional surface indicated by the hand here would be an angular unconformity. Then as we move towards the top of the sequence, we see another irregular shaped line which represents a buried erosional surface between the limestone in yellow and layer N. This would be called a disconformity because the rock layers below are horizontal to the rock layers above the erosion surface. If you look right on the very tip of rock unit A, again, this would be an igneous rock unit which shows erosion at these 2 points. Therefore, that would be termed a nonconformity. And lastly, right near the surface between rock units K, B, and F, we see another erosion surface where the layers below are inclined at an angle. Therefore, the unconformity between rock unit K and rock unit F would be an angular unconformity. Another question that could be asked is to list the rock layers from oldest to youngest. And in this case, we would see that the lower rock units down towards the bottom of the diagram will be older. Okay? The rock units above, up towards the top, will be younger. Now I will demonstrate this question in examples that follow. Let's have a look at a sample public exam question. Use the diagram below to answer the questions that follow. Part 1. List the geologic events represented by letters A to K, from oldest to youngest. So if we look at the diagram to the right, we'll notice that, again, contact metamorphism is missing on the diagram. So I'll just draw that in, because the plus signs here is represented by granite, and we know that granite is an igneous rock. So that should have contact metamorphism traveling all the way down alongside the outer edge of the granite. So when the granite intruded the rock layers, it burned the rock layers that intruded. Also, layer G is basalt. And basalt is a volcanic rock that generally forms on the surface of the earth. So the sides of rock unit G on both sides, all the way up, should have the X's representing contact metamorphism traveling right to the surface. So quickly, I'll just put in a couple of X's going up the side, which represents contact metamorphism. And also when it spills onto the surface, we will see the lava flow actually burning the top of rock unit A. So we also see contact metamorphism along the bottom rock unit G, where it comes in contact with rock unit A and all of the rock units that it touches while migrating to the surface. So we see contact metamorphism, the entire length, right up along the sides of rock unit G. So to go back to our question, list the geologic events represented by letters A to K, from oldest to youngest. So when we look at our diagram, we need to look at the oldest events. Generally speaking, if an intrusion cuts across other rock units, then the intrusion, in this case E, would have to be younger than all the layers it cuts across. So according to the law of superposition and original horizontality, sedimentary rock layers J, L, H, F, and the limestone, in this case, which is represented by D, which we can barely see, those all had to be laid down first. So therefore, we will put those from oldest to youngest. So in our diagram, or in our listing, we would write down the oldest layer would be J, the next layer in the sequence would be L, then H, then sandstone F, and finally this final sedimentary layer in that sequence will be the limestone, represented by letter D. Once we go back to our diagram, we see that layer J, L, H, F, and D were laid down. At some time they must have been affected by compressional forces, and all the corresponding layers were tilted on an angle. After they were tilted, layer E would have intruded. So that would be the next layer in our sequence. So the next layer in our sequence will be rock unit E, which is the intrusion. If the contact metamorphism had a letter on it, then we would put that into our sequence next. But seeing that the contact metamorphism is not labeled, then we don't need to include that in our diagram. Now, extending from the bottom of the diagram towards the top, we notice that G intrudes through E, and it also intrudes through layer D, the limestone. But it keeps going right to the surface. Seeing that it makes it to the surface, rock unit G would probably be the youngest. So the next in sequence would be the erosional surface of all of the inclined layers, sedimentary layers, and also the little bit of erosion over on the left side of the diagram of the granite. So this erosion surface is represented by K and would represent the next event in the sequence. So our next event would be the erosion, which is an angular unconformity, represented by K. So the erosion surface will be next. On top of the erosion surface, we have rock layer C, rock layer B, and rock layer A. So these three rock layers would be the next three in our sequence. So we put down rock layer C was deposited, followed by rock layer B, which is sandstone deposited, and followed by rock unit A, which is a conglomerate being deposited. And finally, we have G, which intrudes all the rock layers and spills it onto the surface as a lava flow. So our last rock unit to be formed in this sequence would be G. Next, we move into and look at question 2. Question 2 states, which type of nonconformity is represented by K? So if we come back to our diagram, we stated that all of the layers, the sandstone, the coal, the conglomerate, the sandstone, and the limestone, are all inclined at an angle, and then they are eroded by layer K, or rock unit K. So K represents the erosion of all these layers at an angle. So therefore, K would be called an angular nonconformity. And last question 3. Explain how you know which letter identifies the oldest igneous rock unit. So if we look at the oldest igneous rock unit, and if we go back to our listing of the rock units from oldest to youngest, we see that J is the oldest. And J is located down to the bottom right of your diagram. And because of the law of superposition, we know that if these rock layers were relatively undisturbed, then J would have been laid down first, followed by L, followed by H, followed by F, and so on. So the law of superposition would state that the layers on the bottom will be older than all the layers above it, and also they would be older than any layer that cuts through it, which in this case will be the rock unit G and rock unit E. So the law of superposition would state that J, in this case, would be the youngest rock unit. Let's look at another example. Example number 2. It says, determine whether a rock unit represents a buried lava flow or an igneous intrusion. When determining the difference between a buried lava flow and an igneous intrusion, and in this case, we see rock unit A, which cuts up through many of the surrounding rock units, but it don't quite make it to the surface. But the question at hand is, did this rock unit make it to the surface, and then rock unit J be buried on top of it at a later time? Or did rock unit or intrusion A not make it to the surface, and it intruded between these two rock layers indicated by the hand? The answer lies in the contact metamorphism. So contact metamorphism is key to determine if you have a buried lava flow or if you have an igneous intrusion. A buried lava flow would only have the contact metamorphism beneath the igneous rock unit, whereas an igneous intrusion would have the contact metamorphism both beneath and above the igneous rock unit. So if we go back to our diagram and we look at the igneous rock unit A, we see contact metamorphism represented by X's all the way up through the sides of rock unit A. But we also recognize that the contact metamorphism is located above rock unit A, which suggests that rock unit A did not make it to the surface, but instead intruded in between the rock layers above and below, therefore burning rock layers below and also burning the rock layers above. This burning is what we call contact metamorphism, and seeing that we see contact metamorphism both above and below the igneous intrusion A, therefore it must be an igneous intrusion and not a buried lava flow. Your turn. Take the time now and complete the following questions. Solutions will follow. You can pause your recording now to prepare your answers, and then restart your recording to find the answers. Questions. Use the diagram to answer the questions 1 and 2. Question 1 states, does A represent an intrusive feature or an extrusive feature? In question 2, it says arrange all letters in the order in which they occurred, beginning with the oldest. When we look at the solution, rock unit A represents an intrusive rock unit. The presence of contact metamorphism surrounding the entire igneous rock unit suggests that magma intruded the surrounding rock units where it baked the rocks that it had come in contact with. In the diagram to the right, it's hard to see, but we do see evidence of contact metamorphism on the top of rock unit H and also on the bottom of rock unit H, which suggests that it is an igneous intrusion and it did not make it to the surface. When we look at arranging all the letters in order in which they occurred, beginning with the oldest, we need to go back to our diagram and start from the bottom. Here we notice that rock unit R, followed by rock unit M, followed by rock unit P, followed by rock unit X, and finally rock unit S. These rock units were all laid down horizontally at one time and were later folded into a tight fold. So if we were going to state the oldest rock units, we would have to start with the sandstone, rock unit R, followed by limestone, M, followed by P, which is conglomerate, followed by shale, which is rock unit X, followed by S, which is a bit of sandstone. And then once we notice all those rock units, we got to look at the fault that cuts all the rock units. That would be represented by I. Now, the fault that cuts down through all the rock units do not pass through rock unit A. This suggests that rock unit A must have come after fault I because it cuts fault I off. Therefore, the next event in the sequence would be fault I. After fault I, we could have rock unit A. Now, there's one thing that we got to note here when we look at rock unit A. Rock unit A do cut fault F. Therefore, it must come after fault F. But it don't come in contact with any of the surrounding other rock units. So rock unit A could have occurred any time after the erosion, represented at the top of the folded layers here, represented by B, or any time after H, which also passes up through these rock units. So if you included rock unit A at any point hereafter, it would be correct, because we really can't tell if it came before or after Q, F, H, C, or J. But the only thing we do know, it do come after F, because it cuts the fault F, or sorry, it do come after the fault I, because it cuts the fault I. Next in the sequence, we look and we see all of these rock units are eroded. So the next event that we would have to list will be the erosion, which would be B. So erosion B would be next, followed by deposition of limestone Q, followed by deposition of the shale F, and after the deposition of the shale, we see that we have an igneous intrusion, or an igneous rock unit, H. The question is, did it make it to the surface and layer C and J deposit afterwards, or did it intrude between F and between layer C? And if we notice, we have contact metamorphism both above and below. This suggests that layer C must have been there before in order for the igneous intrusion to have burned it. So therefore, C would be the next rock unit in the sequence. So after layer F was laid down, we would have had layer C laid down, then layer J, followed by the intrusion of H, because we see contact metamorphism both below and above H. That would suggest that it came after rock units C and J. And lastly, associated with rock unit H is the contact metamorphism represented by letter E. So this would be the last event in the sequence.